So in this chapter, we're going to be working on exponential functions and logarithmic functions. In 4.1, we're going to talk about exponential functions. So the legend goes that, back in olden times, in China, there was the emperor, and he was out, walking about the city, and a cart's going to run him over, and a peasant saves him. He saves the emperor's life. Okay, so the emperor says, you can have, half of my kingdom. And the peasant says, no, I don't want that. Take a checkerboard and put 1 grain of rice on the first square and then double it for each square. And there's 64 squares on a checkerboard. Well, in the end, the peasant gets everything because the emperor runs out of money because there's so much rice by the end of the 64th square. Okay? So this is an example of an exponential function. Something doubling every time is going to increase at a quick rate, okay? So these are the types of functions we're going to talk about. So I don't know what you want to write for exponential functions, but that's just a little example. So some terminology. Percent change. When we talk about percent change, it's based on a percentage. Well, that makes sense. So, let's say you are going to increase by 30%. Say you want to increase your sales by 30%. Well, then it depends on what your sales are before you can figure out that increase, right? Okay. So that's what we're talking about. It's the percentage based on, it's the increase based on a percentage. And that percentage is on an amount, an original amount. And that's my abbreviation for amount. Okay. Exponential growth, that's what we were talking about when we were saying about the emperor and things doubling. Okay. So what happens is, let's say you have 100 grains of rice, and then it doubles to 200, and then you have 400, because each one's going to be, and then 800, and then 1600. See, each time it's doubling, okay? So that's what we're talking about growth. So in 1, 2, 3, 4 steps, we're already up to 1600, okay? Now, you can also have exponential decay. Let me go back to growth for a minute. Growth, exponential growth, we see that sometimes in population growths, where the population is increasing. Inflation, unfortunately, that's usually a an exponential growth model. I'm trying to think. Compound interest. Okay, so that's a nice thing. You put some money in the bank, and over time, you're going to get, more money based on this compound interest idea. They say when you're young, if you just start out with a little bit, over time, by the time you're ready to retire, you're going to have, a substantial amount of money. That's all based on exponential growth models. Okay. Exponential decay, you can have a population that's decreasing. Some countries, their population is decreasing, so that could be an exponential model. We also see examples like radioactive material. So it's you have less of the material over time. That is an exponential decay model. They talk about half-lives with exponential decay with radioactive material. Okay. So those are just some examples. All right. So exponential growth or linear growth. So let's say we have exponential growth, 2 to the x power. Okay? And we'll talk about that. So then say you have 1 for x. Well, then that would be 2. So I'll do this kind of little table of values here. So if I put in 1 for x, I get 2. If I put in 2, I get 4. If I put in 3, I get 8. If I put in 4, I get 16. And if I put in 5, I get 32. So we're raising it to that power, and see how the number jumps up quickly. Now let's say I do a linear model. So this is exponential growth right there. And now let's do a linear model. So what we're going to do is we're going to take x and go 2 times x. So we put in 1, 2, 3, 4, 5. And what do we get? 2. 1 times 2, 4. Starts out the same. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. So look at the fifth step here, or when x is 5, you see a difference, a pretty significant difference between 10 and 32. And that's the difference between an exponential growth and a linear growth. Okay, so now we're going to talk about the general form of an exponential model, or an exponential function. All right, so we're going to have f of x equals a b to the x power. Okay, notice that the exponent is in the variable is in the exponent. Okay, that's really important. That's what makes it in part an exponential function. Okay, a can't be 0. Okay, so that's just a thing that a cannot be 0, because then you just have 0 and it wouldn't be an exponential function. B is the base, and that one's a little bit trickier. It can't be 0, and so it can't be 0, and it can't be 1. Because if it's 1, if you keep raising 1 to a power, it's just gonna still be 1, okay? And then things happen. If b is greater than 1, then you're gonna have a growth. Sorry, I wrote increase, but it's a growth model. But if b is between 0 and 1, it will be a decay model. And b has to be greater than 0. Okay? So put all that information in there, and a lot about b there, but we'll see some examples and that will help. Okay. Just a little bit more here. So going back to our exponential model, we had, if we wanted to graph it, so I'm talking about the table of values that I just did right over here. So it went through the point, we didn't put in 0, but we could have. It would have been 0, 1, and then, you probably want to see that, huh? I scrolled up. So let me go back to this, x, 2 to the x. Let's extend it a little bit. If I put in 0, I'm going to get 1, right? So 2 to the 0 would be 1. What happens if I put in a negative number? Well, if I put in a negative number, I'm going to get 1/2, right? Because you have 2 to the negative 1, and by definition, that's 1 over 2, okay? What happens if I put in, well, I'm out of room, but negative 2? Well, that would be 2 to the negative 2. That's going to be 1/4. And I want to do these examples so you can see what happens when the exponent is negative. Okay, so you can have x be negative. It's b that can't be negative. Okay, so then you get negative 1 1/2, negative 2 1/4. Are we ever going to get this to be 0? No, it's not going to be 0. It's going to approach 0 as it gets more and more negative, but it's not going to equal 0. Okay. Now, what happens on the other part of the graph? When we put in 1, we had 2. When we put in 2, we had 4. And then when we put in 3, we jumped up here to 8. And then I'm kind of out of room on my graph paper. But notice that the curve is going up very quickly. Kind of missed the points there. And then it's going to run asymptotic to the x-axis. Okay? So meant to erase that. So that's what an exponential graph looks like. Depends on the base, how quickly it's going to go up, or, if the base is less than 1, it'll look different. But for an exponential function where b is greater than 1, it's going to look something like that. And you do have an asymptote right here at the x-axis. Okay, so this would be an asymptote. Okay, so I think that's all we're going to say in this video. So just getting us used to exponential functions and what they do. Okay, before we leave this one, let me talk a little bit more about some features on the graph. So let's make sure we have this f of x is equaling a b to the x. Now, some of our ideas from transformations, those still hold. So a could reflect, if a were negative, it would reflect it about the x-axis, the graph. And what do we have for our graph right here, this one right here? Well, we have a y-intercept at 0, 1. There's no x-intercept, none. We have the asymptote. By the way, the equation for the asymptote is y equals 0. And what about the domain and the range? For our example, we have the domain is all real numbers. And that's going to be true for our exponential functions. I don't think that's going to change. The range, though, that might be dependent on a, if a is positive or if a is negative. In our example, our range is from 0 to infinity if a is greater than 0. If it were reflected about the x-axis, then it would be from negative infinity to 0 if a were negative, if a were less than 0. Okay, so I think that's all the details I wanted to put in about the graph.